The goal of this experiment is to record the force, acceleration and velocity of the smart cart as it travels up the incline with respect to time. The objective is to demonstrate the concept of kinetics in particles. For all of these experiments we are treating the smart cart as if it was a particle. We are going to compare the experimental results to our theoretical results and explain why there is a difference between them. For both of these experiments we are treating friction and aerodynamic forces as if they are zero, even though realistically both of these apply to the cart in negligible amounts. For the first experiment we are also treating the magnetic damping force from the bumper to be zero, and therefore the cart should undergo constant acceleration. The first experiment involves the cart going up the slope from the tension force provided by the cable attached to the weight. Given the parameters of the experiment, we can calculate that we expect the continuous acceleration of the cart to be 2.34 meters per second. This is calculated by determining the force provided by the suspended mass and the force that gravity applies to the cart, and in calculating the total acceleration. When we compare our theoretical acceleration to our experimental acceleration, we notice that our theoretical acceleration is higher than our experimental acceleration. This trend continues for the velocity and the displacement as well. The difference between our experimental values and our theoretical values are probably because our assumptions of no friction and no air resistance are not good assumptions. This is shown by the fact that our theoretical values are higher than our experimental values, yet both of the trends have the same shape. The rise in acceleration at the beginning of our data is likely due to the fact that we didn't release the cart instantaneously, and we concluded that the small oscillations in the data may be a result of the suspended mass swinging as it's moving down.
In our calculation for the estimate of the mass of the bumper, we took the average force and divided it by the average acceleration of our recorded results. The reason we did this is because when we zeroed the car, it was at the bottom of the track stationary. That means the weight forces of both bodies, the cart and the damper, that are already acting during that process, they became zero and became a base of the force sensor reading. Thus, the force sensor reading arose from the acceleration of the two bodies, and the forces between that is due to the acceleration on the center of mass. Thus, we can just take the formula F equals ma and rearrange it to m equals F over a, and we took the average force and the average acceleration to calculate the mass of the bumper.
Yeah.
In the second experiment, the bumper is upside down, which means the magnets are closer to the track, which means that the force that the magnets put onto the cart is greater and significant, which is proportional to the velocity of the cart. The objective of experiment 2 is to demonstrate dampening in a system by showing the comparison between the experimental data and our theoretical calculations, and see how including the magnetic force changes the motion of the cart. We can see in the experimental data for experiment 2 that the acceleration is decreasing over time, which is expected as the force the magnets apply to the track is relative to the velocity of the cart. Since the mass of the bumper is assumed to be negligible, the internal reaction force on the force sensor will be totally the result of the magnetic forces. Thus the value of k can be found by taking the gradient of the force over velocity. As k is proportionately constant, the line of best fit must go through the origin for this. To calculate the theoretical acceleration on the cart for experiment 2, we considered the forces being applied to the cart from not only the rope and gravity, but added the force that the magnets would apply to the cart, which was a function of the velocity of the cart. We then used our kinematic equations to convert this to a function of time, and from there we integrated it twice in order to get the velocity and the displacement of the cart. For the second experiment, we see the trend of our experimental values being lower than our theoretical values appear again. This is largely due to the fact that we once again have assumed that there's no friction, which once again is probably a bad assumption. Because of this, all our data is lower than our theoretical values because our kinematic equations did not account for friction. In conclusion, the dampening force of the magnet dramatically changes the motion of the cart. The most significant fact is the fact that acceleration will be decreasing over time as the magnetic dampening force increases as the velocity of the car increases. In theory, if the track went on forever, eventually the magnetic track would get to a terminal velocity, whereas the constant acceleration experiment would keep accelerating.